This is Chapter 12, Variable Frequency Network Performance, Sections 1 to 2. In Sections 1 to 2, we're going to look at variable frequency response analysis in terms of network performance as a function of frequency and a transfer function. Then we're going to relate that to our sinusoidal frequency analysis that we've been doing, but now with Bode plots to display frequency response data. Section 1, Variable Frequency Response Analysis. In an AC steady-state analysis, the frequency is assumed to be constant. So, for example, we consider the frequency as a variable here and examine how the performance varies with frequency. So, for example, the variation in impedance of a basic component, well, a resistor has the same value no matter what frequency we have. And therefore, if we plot it as a function of frequency, it's a straight line. The phase, if you will, of a resistor is 0 because it is a totally real component. And as a function of frequency, it is also a straight line at 0 degrees. For an inductor, we know the impedance is j omega L, or if you will, a magnitude of omega L at an angle of 90 degrees. If we plot the impedance as a function of frequency, it's a linear or straight line. And if we plot the phase, it's a horizontally constant line at plus 90 degrees in this case, as a function of frequency. For the capacitor, ZC is equal to 1 over j omega C, or the magnitude is 1 over omega C at an angle of minus 90. Likewise, we can plot the frequency response of the magnitude, and we find out it's an inverse function. At 0 frequency, it's infinity, and at very large frequencies, it gets progressively smaller. The phase, though, is a constant, minus 90 degrees at all frequencies. Let's look at the frequency dependence, though, of a variety of circuits using resistors, inductors, and capacitors. So here we have the series RLC network, 3 components in series, and we're interested in the equivalent impedance. We can write the equation for the impedance, since it's the sum of 3 impedances, R plus j omega L plus 1 over j omega C. We can also recast that, putting it all over j omega C, and we end up with a numerator term, which is the quantity j omega squared times LC plus j omega RC plus 1 divided by j omega C. We can also normalize that by multiplying top and bottom by minus j, and we end up with omega RC plus j, the quantity, omega squared LC minus 1 divided by omega C. The magnitude then would be the magnitude of that impedance, and that's the square root of omega RC squared plus quantity 1 minus omega squared LC, quantity squared, divided by omega C. That's essentially just a squared plus b squared, because we have a real part and an imaginary part in the numerator. So we'll take a squared plus b squared, and we'll take the square root. And of course, the denominator is wholly real at omega C, so that we don't have to do anything with that. If we were to plot it, it's a little bit harder to plot, but we have many computer-aided tools in electrical engineering. And the plot of that particular magnitude looks like this. At very low frequencies, it approaches infinity, mainly because the capacitor is acting now like an open circuit or a very high impedance. And at progressively larger frequencies, it will go back to being essentially a linear line because we'll have an inductor taking over. The capacitor has very minimal effect. There is a minimum value, though, at which the function minimizes, and that's where the frequency omega, or 2 pi f, is equal to 1 over the square root of LC. The angle of this impedance, Z equivalent, is the arctangent, of course, of the 2 components, namely omega squared LC minus 1 divided by omega RC. And that's because the quantity omega c in the denominator is a wholly real number. So we're basically getting the angle from the complex part in the numerator, and the denominator essentially is a scaling or a cofactor part. And the phase angle then looks like this. It starts at minus 90 degrees towards zero frequency. That's because the capacitor is primary. Passes through zero at some point, and then essentially levels off at some intermediate value as a function of frequency. We can simplify the notation because we often have the term j omega. We can simplify the notation by substituting the variable s wherever we see j omega. So for example, the quantity j omega squared becomes s squared, and the quantity j omega just becomes s. So we end up with z equivalent of s is s squared lc plus src plus 1 divided by sc. We can have simplified notation for basic components. For example, for a resistor, Zr of s is just R. For an inductor, Zl of s is just Sl. And for a capacitor, should be Zc of s is 1 over Sc. In all cases that we've studied and can study, the impedance will be the form of rational polynomials, a numerator polynomial, and a denominator polynomial of various orders. The order of a polynomial, of course, is given by m in the numerator and n in the denominator. Circuit elements RL and C and dependent sources are real. Then the expression for any voltage or current will also be a rational function of S. To show this, let's try a learning example. V sub S is equal to 10 angle 0. Capacitor is 2.53 millifarads. L is equal to 0.1 henries. And R is equal to 15 ohms, and we're interested in the target variable V0, which is the voltage across the 15 ohm resistor. We can convert the capacitor to 1 over Sc, the inductor to S times L, and the resistor remains R. We can then write the formula for the solution and substitute the values in later, but the solution V0 of S would be the numerator R divided by R plus SL plus 1 over SC times V sub S. And that's because it's a voltage divider. So we put the voltage dividing impedance R divided by the sum of the impedances. In this case, R plus SL plus 1 over SC. We can now rationalize this particular equation by multiplying top and bottom by SC to clear out the fraction. So the numerator becomes SRC, the denominator becomes S squared LC plus SRC plus 1 times V sub S. When we've done steady-state AC problems, S was actually j omega, and it can remain that too. We can make a substitution at any point, and therefore we could get V0 is equal to j omega RC divided by quantity j omega squared times LC plus j omega RC plus 1 times V sub S. Substituting in the values for C, L, and R, which are just numerical values, we then get an expression now for V0. And obviously any computer-aided tool can be used to effectively compute frequency response characteristics as a function of omega and get us and allow us to plot it easily also. So MATLAB is a typical tool for doing that. We can use MATLAB to compute the magnitude and phase information and help automate our computations. So given a polynomial like V0 of S as a polynomial in the numerator and denominator, we can then write in MATLAB num, just a nominal name of a variable, equals, notice the square brackets, in this case the coefficients of the polynomial in the numerator, with a semicolon terminating, and then den, just a variable name for the denominator, again the square brackets and a list of components of the polynomial terminated by a semicolon. And we can call up a MATLAB built-in function called freqs, or freqs, whose arguments are numerator comma denominator, and that can be used then to display the magnitude of phase as a function of frequency. If you don't want to use commas, MATLAB will accept a white space, a single space, to separate the numbers in an array. So let's take our example, which we've just found for the output voltage as a function of a frequency. And of course, we have radian frequency, omega. But we notice that we do have an A1 component in the numerator, and that's all. And in the denominator, we have a B2 component and a B1 component, and that's all. There is a B0 component, of course, but that's given as 1, so we're okay with that. It's not even a function of any of our variables, but we can certainly include that as one of the fixed terms, B0. So in MATLAB, then, you would write that, and this is one form of it. Here we're using commas to separate the variable names. Notice that we have just 2 in the numerator. There is no A0 term, so we've put actually a 0 in there to indicate that there is no A0 term. That helps to identify the terms, of course, because MATLAB is looking for an A0 term. So notice that we did put an A0 equals 0 term there. And in the denominator, we have 3 terms, and of course we do have a B0 term because it has to be 1. And then we indicate to MATLAB to solve this by typing freq s num comma den. The missing coefficient then must be entered, as I said, as zeros. We can also use spaces rather than commas. However, you have to be careful in some applications, and usually commas gives us a safe path to make sure that we've actually used it. So for example, in freq s, we have to have a comma and not a space. Here are the MATLAB plots that results on a log-log scale for the magnitude on the top and for the frequency on the bottom. It's a log-log plot on the top because we want to have a large range of magnitude, but it's a semi-log vertical, linear vertical plot, and a log plot horizontally so that we can see the range of frequencies, but we don't want a log plot for the angle. This is quite convenient to be able to do something like this, of course. So here we have an example of a stereo amplifier. We would like it to have a low frequency response in the vicinity of 100 Hertz and a high frequency response somewhere above 10 kilohertz, but certainly below 100 kilohertz. So we can pick a specification. In this case, we would like it to be relatively flat or flat frequency response between 50 Hertz and 15 kilohertz. The amplifier that we would want to analyze looks like this. It's a typical example of an active circuit. We have a capacitor input with the resistor input, and that develops Vin as a function of time from a source. We have a dependent source which takes the value of Vin and multiplies it by 1000. That makes it an amplifier. And we have an output R0 and a capacitor in parallel with the output C0 to give us our output voltage V0. And typical values for Rin would be 1 mega ohm, Cn would be about 3.18 nanofarads, R0 would be 100 ohms, and C0 would be 79.58 nanofarads. So that's what we postulate would be this amplifier. Taking that as our model, we could do a frequency domain equivalent circuit by reducing the capacitor to 1 over SC, the resistors to R, and we end up with this particular circuit now as a function of S. And the gain then is V0 of S, the output voltage, as a function of S, divided by Vs of S, which is the input voltage. We'll call that the voltage gain. That's also, since V0 can be written, it's also Vin times V0 divided by Vs times Vin. We've multiplied top and bottom essentially by Vin. And Vin is nothing more than Rin times Vs divided by Rin plus 1 over S Cn. Making those substitutions, we get V0 of S is 1 over SC0 divided by 1 over SC0 plus R0 multiplied by the dependent voltage source gain, which is 1000 Vn. Or, if you will, bringing those terms together, we can calculate the gain then as S times Cn Rin divided by 1 plus S Cn Rin times 1000 as a gain, multiplied then by 1 over 1 plus S C0 R0. Bringing the products together for the terms that we just saw, we can multiply Cn, which is 3.18 nanofarads, by Rn, which is 1 megaohm. We get 3.18 times 10 to the minus 9th times 10 to the 6th for 1 megaohm, and we want 1 over that. We get approximately 100 pi. Doing the same thing with C0R0, 79.58 nanofarads times 100 ohms, we get approximately 40,000 pi for the 1 over C0R0 term. 100 pi is about 50 hertz, and 40,000 pi is about 20 kilohertz. We can then recast this then in that terms, so the equation becomes G of S is equal to S over S plus 100 pi times 1,000 times 40,000 pi over S plus 40,000 pi. So the magnitude of S then goes between 100 pi and 40,000 pi, and therefore G of S can be rewritten approximately as S over S times 1,000 times 40,000 pi over 40,000. We're just making a simplification, if you will. And therefore we can plot the actual response, which is not going to be flat because we only have a very simple amplifier here, against the specifications or the required response, and that's what it would look like. The term that generates the component at low frequencies is S over S plus 100, and the term that generates the high frequency roll-off or decrease in amplitude is the 40,000 pi divided by S plus 40,000. Frequency-dependent behavior is caused by the reactive elements because they have the frequency-dependent component. When voltages and currents are defined at different terminal pairs, we can define something called a transfer function. So if our input is a voltage and our output's a voltage, we'll call that a voltage gain, and we can give it a symbol like G sub V of S. If we have an input that's a current and our output's a voltage, that's called a transimpedance, and that's given the symbol Z of S. If a current is our input and a current is our output, that's a current gain, and we'll call it G sub I of S. And if a voltage is an input and a current is an output, that's a transadmittance, and we'll give it the symbol Y of S. If voltage and current are defined at the same terminals, we can now call it a driving point impedance or admittance. So here's an example. V1 of S develops a mesh current of I1 of S through R1 and SL. And then we have a current I2 of S with a capacitor 1 over SC and an output voltage V2 of S across R2. Therefore, YT of S is equal to I2 of S divided by V1 of S. That would be a transadmittance transfer function. And GV of S, defined as V2 of S divided by V1 of S, would be called a voltage gain. To compute the transfer functions, we must first, of course, solve the circuit, and any technique that we've learned up to this point is certainly acceptable. Let's continue our example that we started. The textbook uses mesh analysis, and here we'll use Thevenin's theorem. We'll put a big blue box around the circuit that we'll consider the Thevenin equivalent circuit, and that, of course, is not including the terminals and the load resistor R2 and the target variable V2 of S. The open circuit voltage then consists of SL divided by SL plus R1 times V1 of S, because the capacitor 1 over SC does not participate. It's an open circuit. The equivalent impedance then of the Thevenin equivalent circuit is the series capacitor 1 over SC, here it does participate, plus the parallel combination of R1 and SL. That is equivalent to 1 over SC plus the parallel combination becomes SLR1 over SL plus R1. Or we can straighten out that fraction by writing ZTH of S is S squared LCR1 plus SL plus R1 divided by SC quantity SL plus R1. So now we have our circuit as a Thevenin equivalent. which is a good way to solve the circuit. And we have our load resistor R2 put back in place across the terminals. And we have our target variable V2 then as the voltage across that resistor. So I2 of S is VOC divided by R2 plus ZTH of S. We could substitute in what those complex terms look like and straighten them out. Straighten out the fractions, especially the denominator, which is quite complicated. So therefore we end up with a admittance transfer function, YT of S, as S squared LC divided by S squared quantity R1 plus R2, close quantity LC, plus S quantity L plus R1 R2C, close quantity plus R1. And GV of S, the voltage gain, would be V of S divided by V1 of S, which is R2 I2 of S times V1 of S, or if you will, R2 YT of S. So given an arbitrary network function, whether it's a transadmittance, it's an impedance, it's an admittance, it's a transconductance, it will still be a polynomial in S on the numerator and denominator. We can often factor polynomials easily, sometimes with tools that will allow us to do the factorization to become a product of first order terms. So when we do that, we end up with the transfer function, the arbitrary network function, h of s, being some constant k0 multiplied by a bunch of terms, where the terms in the numerator are called the zeros of the network function. That meaning that when s equals z1, for example, that would be 0 because it's s minus s1, and therefore the entire numerator would be 0. Likewise for s equals s2 all the way to s equals sm. Meanwhile, in the denominator, if s is equal to p1, it'll be 0, but since we're dividing by 0, it'll be infinity. That's called a pole of the network function. So s equals p1 would be a pole. Likewise, if s equals p2, that'll be a 0. That will also be a pole all the way to s equals pn. The network function then is uniquely determined by its poles and zeros and its values at some other values of s, which can be then used to compute the gain. At a value of s at a 0, the answer is 0, and a value of s equal to the pole, the answer is infinity. So obviously we would want to calculate it at other locations where that does not occur to come up with other values. So let's take an example here. What if z1 is minus 1, and what if the pole p1 is minus 2 plus j2, and the pole 2 is minus 2 minus j2, and we'll say that h of 0 equals 1. That is, letting s equals 0, we end up with a value of 1. We can then write what would actually happen. H of s equals k0 times s plus 1. Remember, the 0 is s minus z1, and z1 is minus 1. That's why we get s plus 1. And then we end up, likewise, in the two poles in the denominator, as quantity s plus 2 times minus j2 times quantity s plus 2 plus j2. And that's because we reverse the sign, s minus p1 and s minus p2. We would then, we could also then multiply out these terms, and we'll get k0 times s plus 1 over s squared plus 4s plus 8. Since we said that h of 0 is equal to 1, that means that k0, substituting s equals 0, would be k0 times 1 over 8 equals 1. So therefore, by definition, k0 has to be 8 as a result, so that we would get h of s equals 1 at s equals 0. So here we have our example that we've looked at before of the hi-fi amplifier. We have it in the time domain. We have it in the representation in the S domain on the top, time domain in the middle. We can find I of S as the input current. We can find Z of S as V of S divided by I of S then. Using Kirchhoff's voltage law, we find that V of S is Rn I of S plus 1 over SC I of S. Or Z of S is then Rn plus 1 over SC in. We can replace their numerical values, and we find out it's 1 plus 100 pi divided by s megohms. We can find the pole and zero locations and the value of K0, and for the voltage gain, G of S equals V0 of S divided by V of S. V0 of S is the output. So we have our general form for the zeros and the poles, if you will. For this case, the gain can be shown to be, and we've done that before when we did it earlier. So therefore, if we look at the particular representation, we find out that since the numerator term only has an s in it, there is a single zero, namely z1 equals 0. But the denominator has two terms in it, and those terms are 100 pi, which is approximately 50 hertz, and 40,000 pi, which is approximately 20,000 hertz. So our P1s, at least in hertz, our P1 equals minus 50 hertz, and P2 is equal to minus 20,000 hertz. Substituting in those numbers and the expected gains, we would find that K0 is about 4 times 10 to the 7th pi as a result. This is section 2, sinusoidal frequency analysis. Here we have a general description of a circuit as a transfer function h of s. The circuit is represented by a network function. To study the behavior of a network as a function of frequency, we can analyze the network function h of j omega as a function of omega. And there are various ways to do that, and we'll take a look at a few of them. The notation that we're going to use, for example, is m of omega, the magnitude, is the magnitude of j omega, and phi of omega is the angle of h of j omega, or if you will, h of j omega is m of omega e to the j phi of omega. That's just as a way of representing the system function, the network function. The plots of m of omega, phi of omega as a function of omega are generally called magnitude and phase characteristics. We already saw some examples of this. And if we reduce those to using logarithmic plots, 20 to log to the base 10 of m of omega versus log to the base 10 of omega, and phi of omega versus log to the base 10 of omega, they're given the name Bode plots by the first individual who actually promoted them. Originated as a measure of relative or radio power. So for example, power 2 in decibels over power 1 would be written as 10 to the log of P2 over P1. These are now powers in watts, for example. Power is I squared R, or V squared over R. So P2 in dB over P1 would be 10 to the log of V2 squared over V1 squared, or if you will, 10 to the log of I2 squared over I1 squared. However, those square terms can actually be brought outside of the logarithm and multiply the cofactor 10 by 2, and that's how we get V in dB is 20 to the log to the base 10 of the magnitude of V. I in dB is 20 to the log of the magnitude of 10 of I, and G in dB would be 20 to the log of the gain G, the magnitude of the gain G. Later on, when you study communications, you'll find that the actual definition is 10 to the log, because in communications we use power in watts and not voltages or currents. Using log scale, the frequency characteristics of the network function can have simple asymptotic behavior. We can see that very easily then. Instead of being curvilinear, they in fact will be straight lines asymptotically, meaning that its frequency goes on. The asymptotes can be used then as reasonable and efficient approximations to the complex functions. Instead of trying to do a curvilinear curve, we can look at the straight line approximation on a log scale. So here's a complex-looking polynomial with some Greek coefficients that we want to analyze now. There's a frequency-independent term, usually K0, that's no frequency-dependent. There are poles and zeros at the origin with terms like j omega can be raised to whatever power. There are first order terms where we have functions of j omega which are first order. Then we have quadratic and complex poles and zeros which result from second order terms like this, and then they can get even more complicated beyond. The magnitude of j omega in dB is 20 to log to the base 10 of the magnitude of h of j omega. And we also know that log of a times b is log of a plus log b, general definition of logarithms. And the log of n divided by d is the log of n minus the log of d. We could then use that to write h of j omega in dB now as a series of linear coefficients that are added and subtracted. 20 log to the base 10 k0 plus or minus n, 20 log to the base 10 of the magnitude of j omega, plus 20 log to the base 10 magnitude 1 plus j omega tau 1, plus 20 log to the base 10 1 plus 2 eta sub 3 j omega tau sub 3 plus j omega tau sub 3 squared, minus 20 log base 10 quantity magnitude 1 plus j omega tau a times the magnitude minus 20 log base 10 magnitude 1 plus 2 eta b j omega tau b plus j omega tau b quantity squared minus . So it can get quite complicated after a while, but if we substitute in real values, it's not too hard to do. Notice also that the magnitude of z1 times z2 as an angle would be the angle of z1, z2 would be the sum of the angles, z1 plus z2. The angle of z1 divided by z2 would be the angle of z1 minus the angle of z2. Therefore, the magnitude of h of j omega would be 0 plus or minus n times 90 degrees plus the arctangent of omega tau 1 plus the arctangent, etc. Just gets to be term after term based on that description. Display each basic term separately and then add the results to obtain the final answer. Let's examine each basic term then to try to put some understanding to it. So for example, a constant term, 20 log to the base 10 k0, would have a constant magnitude and a constant phase of 0 degrees. J omega to the n raised to some plus or minus capital N power would be the magnitude of j omega to the nth power in dB equal to plus or minus n times 20 log to the base 10 of omega. And the angle would be angle of j omega to the plus or minus n would be equal to plus or minus n times 90 degrees. The x-axis is log to the base 2 of omega, and this essentially then would be a straight line. So the magnitude characteristic can be plotted, and the magnitude characteristic would then have a slope. If we look at the equation for the magnitude then for j omega to the plus or minus n, it has a slope of minus 20 n dB per decade. Decade means increasing by a factor of 10. The phase characteristic remains constant though at a value of minus n times 90 degrees. We can also look at the log magnitude response. If n happens to be a positive number, then the magnitude response becomes a increasing slope of plus 20 n dB per decade, and the phase angle becomes plus n 90 degrees. Let's look at a simple polar zero, 1 plus j omega tau. The magnitude of 1 plus j omega tau in dB is 20 to log to the base 10 of the square root of 1 plus quantity omega tau squared. The angle of quantity 1 plus j omega tau is the arctangent of omega tau. It's actually the arctangent of the y component over the x component. So it's actually the arctangent of y component omega tau divided by the x component, which is 1. So that's why we just have arctangent omega tau. If omega tau is much less than 1, then magnitude 1 plus j omega tau in dB is approximately 0, or having a low frequency asymptote. The angle of 1 plus j omega tau then is approximately 0 degrees. If omega tau is much greater than 1, then 1 plus j omega tau in dB would be 20 to log to the base 10 of omega tau. That's a high frequency asymptote at 20 decibels per decade. And the angle for 1 plus j omega tau is approximately 90 degrees. The two asymptotes meet, both of these asymptotes meet when omega tau equals 1. That's called a corner or break frequency. The behavior in the neighborhood of the corner is a little bit more complicated than just two straight lines, but we can actually determine what they are. At the corner, omega tau equals 1. The asymptotic value would say it's 0 dB. The curvilinear or the non-asymptotic straight line approximation, the actual value is about 3 decibels, and it's off by about 3 dB as a result. If we go an octave above, an octave being a doubling of frequency, so from 1 to 2, omega tau equals 2, and therefore we get an asymptotic value of 6 dB, and the curvilinear or exact value is about 7 dB, and it's off by about 1. If we go an octave below, therefore omega tau equals 0.5, that's 1/2 of 1. Asymptotic value would be 0, and the curvilinear or exact value would be 1 dB, and it's off by 1. Here's the plot of what we've just done as a table, and you can see the curvilinear behavior and the asymptotic straight line behavior is the dotted line. The curvilinear behavior is the solid red line, showing us what the relationship is. The plus 20 dB per decade is called the high frequency asymptote, and we also have a low frequency asymptotic value as a result. The asymptote for the phase angle is plus 45 degrees per decade, and that completes the analysis for a simple pole or zero. Here's that plot presented again for a simple zero and for a simple pole. In these plots, we've actually have the phase angle and the magnitude on the same graph, sometimes confusing as a result. Magnitude scaling is on the left, and the phase scaling is on the right. And we can see they're sort of like inverses of one another between the simple zero and the simple pole. Let's look at a quadratic pole or zero. That means a second order term. The second order term, T2 and dB, would be 20 log to the base 10 of the square root of 1 minus omega tau squared plus 2 eta omega tau squared. The angle of T2 would be the arctangent of 2 eta omega tau divided by 1 minus quantity omega tau squared. If omega tau is much less than 1 again, we'd have a low frequency asymptote of about 0 dB for T2 magnitude, and an angle of about 0 degrees. If omega tau is much greater than 1, we'd have a high frequency asymptote, T2 and dB, which would be 20 log to the base 10 of omega tau squared. And the angle, well, that's omega tau squared is 40 decibels per decade, but the angle is going to be approximately 180 degrees. If omega tau is exactly equal to 1, then the magnitude of T2 in decibels is 20 log to the base 10 of 2 eta, and the angle would be 90 degrees. That's called the corner or break frequency. Omega tau then is equal to the square root of 1 minus 2 eta squared, and therefore the magnitude of T2 in decibels is 20 log to the base 10 of 2 eta times the square root of 1 minus eta squared. The angle of T2 then is the arctangent of the y component over the x component, so that'd be the square root of 1 minus 2 eta squared divided by eta. And generally eta would be less than or equal to the square root of 2 over 2 in order to keep it real under the square root, and that's called the resonant frequency. So here's a plot of a quadratic polar zero. This would be for a representation of various values of eta. Eta equals 0, it basically goes off the scale. Eta equals 0.1, stays on the scale. See 0.2, 0.4, 0.6, 0.8, etc. for different values anyway. And that would be our representation all the way down to eta equals 1, if you will. The phase plot looks similar with a bunch of inflection points because of the arctangent term as a function of eta. And it can get goes through a inflection point of minus 90 degrees at our nominal omega tau equals 1 radians per second. These graphs are then basically turned upside down for zeros, and if you want you can turn them upside down and see the opposite behavior as a result. Let's generate the magnitude and phase plot for a voltage gain transfer function, GV of j omega. That's equal to 10 times quantity 0.1 j omega plus 1 over quantity j omega plus 1 and quantity 0.02 j omega plus 1. We seem to have 1 0 in the numerator and 2 poles in the denominator with a constant term. We want to draw the asymptotes for each term and then bring it together. Now what we can see is, because they're all in standard form, plus 1 in all the terms, we're going to have breaks or corner frequencies at 1, 10, and 50. 1 comes about from the term j omega plus 1, because when omega equals 1, we will have a break or corner frequency. The 10 comes about from the term 0.1 j omega plus 1, because when omega equals 1 over 0.1 or 10, we'll have a break or corner frequency. And finally, when omega equals 1 over 0.02, that's 50, and we'll have our third break or corner frequency. So let's take our standard plot here. We have decibels for magnitude, we have phase angles in degrees on the right, and we have a logarithmic frequency plot across the horizontal. And the first term we'll take is 10, and we'll plot that. Well, 10 is 20 decibels, so 10 in decibels is 20 dB. And it's a constant, and the phase angle for 10 is a constant also at 0 degrees. The next term we'll do is j omega plus 1 as a pole. We know the break frequency is going to be 1. So we draw an asymptote out to 1. We're doing this approximately with straight lines at first so that we can get the general form of it. Since it is a break frequency and it's a single pole, it's going to go off as 20 dB per decade. So notice that that line we've drawn starts at 0 dB, then goes down to minus 20 dB at a decade later. So from 1 to 10 is a decade, and it goes down 20 dB. That's minus 20 dB per decade as a result. Okay. The phase angle, though, goes through minus 45 degrees at 1, the break frequency, and produces minus 45 degrees per decade. So it goes down to minus 90 at 10, and it goes back to 0 at 0.1. From that point, it continues on horizontally, because that's what the break frequency is all about. The next term is now a pole, and we know that the break frequency is at 10. So we draw our horizontal line out to 10, starting at 0 dB, because we don't include gain in these terms. The gain is involved with the constant term 10. So we go 0 dB out to 10, and we draw, in this case, not a pole break frequency going down, but a 0 break frequency going up, and that is 20 dB per decade, plus 20 dB per decade. So notice that it starts at 0 at 10, which is its break frequency, and goes to 20 dB at a decade later. And a decade later is 100. The phase angle does the same. It goes through minus 45 degrees. I'm sorry, plus 45 degrees, because it's a 0 and not a pole, at 10, the break frequency, and will go up plus 45 degrees per decade. So from 10 to 100, it goes from 45 degrees plus to 90 degrees plus, where it basically stops increasing, becomes 90 degrees. So that's 45 degrees per decade. The last term is 0.02 times j omega plus 1. The break frequency is at 50. We have to sort of guess where 50 is, but we're given a fine scale across the top there. So there's our 50, if you will. So we draw a horizontal line out to 50. Now let's ask ourselves, this is a 0. So therefore, being a 0, it should be asymptotically breaking down, which it does. And over a decade, which means from 50 to 500, it will go down 20 dB, minus 20 dB per decade. And notice where the dotted blue line indicates 50 radians, we end up with a minus 45 degrees because it's a pole, and it's going to go down minus 45 degrees per decade, of course. From this complicated looking mess, we then want to draw the composite response by looking at the break frequencies and what those asymptotes represent. Okay, well, the composite response is going to start off, of course, with 20 dB, because that's obviously the first effector. And it's going to stay 20 dB until it reaches 1, where the first pole has cut in at 1. Notice that's going down at 1, minus 20 dB per decade. So our dotted green composite line, since it has no other support, is now going down minus 20 dB per decade. However, at 10, it gets support from the 0, which is going up 20 dB per decade. So something going down 20 dB per decade beyond 10 and up 20 dB per decade beyond 10 essentially cancels. So the dotted green line now stays at 0 dB as a result until it hits the next corner or break frequency, which is at 50. And at that point, we no longer have the cancellation of the plus 20 dB per decade canceling out the 20 dB per decade, but we've picked up another minus 20 dB per decade, so basically it just follows that particular asymptotic result. So the dotted green line is the resultant for the magnitude by taking the different break frequency asymptotic values into account. Same thing with the phase angles. We're going to start off with minus 45 degrees per decade, so the dotted red line is going to follow that. Where it goes to 1, it's now going to get support from the plus 45 degrees per decade, so it's not going to get any more negative as a phase angle, but it's going to stay horizontal until it hits the next asymptotic break, which is down around 7 radians per second or so, which is an additional 45 degrees, negative 45 degrees per decade. So it'll go down slightly. But then it runs into additional support, which essentially cancels that. And now we stay constant, if you will, beyond that point. So the dotted red line becomes the response, if you will, up until the next break point, which then forces it to go down again 45 degrees per decade. So it's a composite effect. Taking each one of these pieces into effect, the phase angle takes on a little bit more tortuous representation than the magnitude does, but it's basically piecing them together. You might want to rerun this particular representation until you see each of the components coming into view and how they're actually drawn as asymptotes followed by composites. So here's the end result, the composite magnitude followed by the composite phase for this complicated circuit. Let's look at this learning example now for GV of j omega. We have 25 times the quantity of j omega plus 1 divided by j omega squared times the quantity 0.1 j omega plus 1. The breaks or corner frequencies occur at 1 and 10, and that's of course because of the 0, which is j omega plus 1, would break at essentially 1 over 1 or 1, and for the pole 0.1 j omega plus 1, it would break at 1 over 0.1 or 10. Let's draw the asymptotes for each one of these. Here's our standard curve. The first term is to take 25 and to draw its decibel representation, and 20, the log of 25, is 28 dB. Of course, it has 0-degree phase angle and 28 dB magnitude. The second term, j omega plus 1, is going to have a break or corner frequency at 1, so it'll be constant 0 dB until it hits 1, and then it is a 0, so it'll break positive 20 dB per decade at that point. Notice it goes from 0 to plus 20 at 10, from 1 to 10. Its phase angle would be minus 45 degrees at the break or corner frequency and do 45 degrees per decade, breaking upwards. So it goes from plus 45 degrees to plus 90 degrees, and then plus 45 degrees to 0 degrees, or plus 45 degrees per decade. And that breaks again, it becomes 90. The j omega squared term is a second order term, and that's going to produce a much more larger slope, and that slope is going to be minus 40 dB per decade. At 1, omega equals 1, it will be 0 dB, because the magnitude of j omega squared at omega equals 1 is 20 to the log of 1, or 0. But it's minus 40 dB per decade, as we see here. The phase angle would be minus n times 90 degrees, so that's minus 180 because n is equal to 2. The last term has a break or corner frequency at 10, so we get our horizontal line drawn out to 10, and since it is a pole, it will break at minus 20 dB per decade at 10, and there's the magnitude. The phase angle goes through minus 45 degrees because it's a pole at 10, and it will go from minus 45 with an additional minus 45 to minus 90, or on the other side of 10 down to 1, it will go minus 45 degrees down to 0, up to 0. We now want to form the composites of this. The first term we'll look at is the constant 28 dB and the minus 40 dB per decade term that are interacting. Well, minus 40 dB per decade goes through 0 at 1, so obviously the dotted purple line would have the same slope, but it would have a magnitude of 28 dB at 1 at that point. From that point, it will pick up some additional support so that the slope is not as great from the 20 dB per decade term, which was breaking at 1, and therefore it goes from 28 dB in that case down to 8 dB. And then it picks up some additional negative slope support from the minus 20 dB per decade term that breaks at 10, so then it starts going again asymptotically lower. The phase angle then starts out at with the first slope, 45 dB per decade up to 1, where it's minus 45 degrees overall. I'm sorry, minus 120, 90 plus 45, minus 135 degrees overall. Stays constant if we just sum up the terms, and then breaks again down to minus 180. So the composite form looks like that. And here's the composite graph then for that particular representation. Magnitude starts off at minus 40 dB per decade, becomes minus 20 dB per decade for a period, and then returns to minus 40 dB per decade. Let's do another learning example where g of j omega is 10 to the 4th times quantity j omega plus 2. That's our 0, divided by quantity j omega plus 10 times quantity j omega plus 100. Those are our two poles. But notice that they're not in standard format. The breaks could be at 2, 10, and 100. You could identify them from that particular form, but it's not a standard form, and it would certainly behoove us to put it in standard form. Putting it in standard form, that equation for g of j omega becomes 20 multiplied by the quantity j omega divided by 2 plus 1, divided by quantity j omega divided by 10 plus 1 times the quantity j omega divided by 100 plus 1. In this form, we do see k0 much more clearly than 10 to the fourth was before, because it's actually 20. You do want to make sure that you can make that algebraic transcription from these two forms and to prove to yourself that their two forms are equivalent. This will become very important for algebraic manipulation when you don't have it in standard form. We need to show about 4 decades, which we can do on a graph like this. The first term we'll take is 20, and we know that's 20 times log to the base 10 of 20. So that turns out to be 25 dB, and the phase angle is constant, 0 degrees. The next term, j omega plus 2, divided by 2 I should say, has a break frequency of 2. And a decade later from 2 will be 20, so it helps to mark those two spots that way. So we put in our asymptotic behavior at 0 dB for a 0, breaking at 10 dB per decade. So we go from 0 to 20, out to 2. We put in our representation of our phase angle for the 0. We get 0 degrees at a break frequency of 2, and then a 45 degree per decade representation from that point. Asymptotic behavior brings it out to 90. Likewise, now the 0 terms, break frequency of 10. So we go out to 10, we break 20 dB per decade. We put in our phase representation at minus 45 degrees at 10. That's our break frequency. And we, of course, go down each decade from that representation all the way down to 100 as a result. And we get our constant phase as a result. The last term, j omega divided by 100 plus 1, has a break frequency of 100. So we draw our asymptotic magnitude out to 100, and then we go 20 dB per decade from 100. Same way with the phase. We're at minus 45 degrees at the break frequency and minus 45 degrees per decade on either side. Now we want to put in our composite terms. So we start with our magnitude, which starts at 25 dB until it hits the first asymptotic break. It will then go up from that point and then essentially level off because there's another break at 10. So the asymptotic increase is then becomes constant by the asymptotic decrease that cancels it until it hits the next asymptotic break frequency where it begins to asymptotically go down again. Phase angle is the same thing as we've seen before, starting at some particular frequency that we have as a summation. We work our way to the first break frequency and then the second break frequency as a result, and all the way down to the end. Let's take a look at this magnitude characteristic. G of j omega is 100 times the quantity 0.02 j omega plus 1, should have a closed parentheses, divided by quantity j omega squared. It is in standard form, and the break frequency is 50, omega equals 50, but the complication is that there's a double pole at the origin because of the j omega squared term. We have to do something about that to begin with. So let's bring together the constant term of 100 and the value of j omega squared. If omega is equal to 10, and then j omega squared is going to be j100, and we should end up with essentially 1 over j, if you will, for the representation of the term. And of course the magnitude of 1 is 0 dB. So here we plot it as 0 dB. But since it is a second order pole, it's going to be going at second order rates, which is minus 40 dB per decade, and therefore we put that through the inception point at 0 dB at 10 at 40 dB per decade. So at 10 it's 0 dB, at 100 it's now minus 40 dB, and at 1 it's back to plus 40 dB as a result. The phase angle representation, of course, is going to be minus n times 90 degrees, so we'll end up with that particular plot as a result. The second term is 0.02 times j omega plus 1, so we end up with a break frequency of 50, as we said. So here's our 50, and following it approximately at 500 would be the other break. We put in our asymptotic behavior. We could put in our break frequency. The graphic is a little off, as you can see. And we have our other asymptotic behavior as a result for phase angle. And we have our same concept, a conceptual idea about what happens there. It's plus 45 degrees at the break frequency, going up at 45 degrees per decade, filling out the phase angle. So the complication was the double pole at the origin, which we handled by grouping it together with the gain term. Once each term is drawn, we can then form the composites. Here's the composite magnitude in green. We hit a break frequency, therefore we pick up a slope change, and it continues on. The same way with phase. We start with the dominant phase term, we then break, and then break again, and that completes the phase. Let's do this learning exercise. G of j omega equals 10 j omega divided by j omega plus 1 times j omega plus 10. We notice it's not in standard form because of the j omega plus 10. But we do know that the breaks occur at 1 and 10, but it would certainly be reasonable to put it in standard form because, as you'll see, the gain term changes. So now we have j omega divided by j omega plus 1, that didn't change, times j omega divided by 10 plus 1. Let's plot it. The j omega term at omega equals 1 will be 0 dB. That's because 20 log to the base 10 of 1 is 0. So here we have it with 20 dB per decade positive slope because it's a 0. So it goes from 0 to 20 dB, from 1 to 10, and from 0 to minus 20 dB from 1 down to 0.1. The phase, of course, is 90 degrees and does not change with frequency. In the case of the j omega plus 1, we have a break at 1, so we go out asymptotically from 0 dB to 1, and then we break at 1, and being a pole, it breaks with minus 20 dB per decade. It goes from 0 to minus 20 dB from 1 to 10. And the phase angle goes through minus 45 degrees because it's a pole at 1, and 45 degrees per decade, minus 45 degrees per decade on either side as a result. So from 1 to 10, it goes down to minus 90, and from 1 to 0.1, it goes up to 0 degrees. And asymptotically breaks. And the last term, we know that it has a break frequency of 10, so we draw asymptotically out to 10. Then we go down 20 dB per decade, so from 10 to 100, it goes from 10 to minus 20. Phase angle goes through a minus 45 degree phase shift at 10, and of course down 45 degrees more to minus 90 to 100, and up to 0 degrees at 1 because it's minus 45 degrees per decade. And that completes the phase plot. Now we're going to draw the composites. Start with the contributing term for the magnitude, which is the slope of the j omega term until it hits the first break frequency, where it gets support from the term that's breaking up, but also the term that's breaking down, as we'll see. So everybody basically compensates for each other, and we now have a constant gain from that point until we hit the next break point, and therefore it'll follow that break because there's no other support, and there is the magnitude plot. For the phase plot, we go along with the first supporting element, which is the asymptotic break that we got from the j omega divided by 10 plus 1 term for the phase angle till we hit the first break point. then it breaks a little bit more, then it breaks a little bit more down to minus 90. So those are the phase representations now in the red dotted line. Now a function with complex conjugate poles. So we have 25 j omega upstairs, and we have j omega plus 0.5 times the quantity magnitude j omega squared plus 4 j omega plus 100 in the denominator. We have to put this in standard form, and the standard form includes the 1 plus concept shown in green there. So again, this is an algebraic manipulation, which I think you must do. It's a lot harder than the first order term, so I think you must do that. Notice that the gain term changes from 25 to 0.5. So here's our representation now of our gain term, 0.5 j omega. First term becomes j omega divided by 0.5 plus 1, because that was not in standard form. Then we have the quadratic term, which becomes j omega divided by 10 squared plus j omega divided by 25, and plus 1, putting it in standard form. Now we go about plotting it, and we can deal with the 0.5 j omega first as a group, and we know what that represents. We can pick the break frequencies appropriately, and the break frequencies appropriately is where does it get 0 dB? It gets 0 dB at omega equals 2. So there it is, 0 dB at omega equals 2. And then omega equals 20, it should be 20 dB greater. And of course, it's 0 dB at omega equals 2. That's because of the 0.5 cofactor that it has out front. So when omega equals 2, you get j omega equals 2, j2 times 0.5 is j1, and then the magnitude is 1, and 20 dB to log of 1 is 0. That's how that works. Phase angle is 90 degrees because it is a 0. The other term is a standard first order term with a break frequency of 0.5. So we put in a couple of different lines. We put in 0.5, 0.05, etc. Kind of hard to figure out which line is which now, but we'll try to figure it out. So our break goes along to the first break frequency, which is 0.5. Omega equals 0.5, and of course it breaks down 20 dB per decade out to 5 because of the numerator 0 term. The phase angle goes through minus 45 degrees at omega equals 5 at 45 degrees, minus 45 degrees per decade, so it goes to minus 90 at 5, and it goes back to 0 degrees at 0.05. And we can fill in the rest of the phase term as a result. The complex representation of the quadratic term is a little bit harder to do, but we'll try. And in that case, we need to know what the break frequency is. And the break frequency can be identified by looking at that term 2 eta tau equals 1/25th, tau equals 0.1, and therefore eta is equal to 0.2. So it tells us a little bit about the performance. These are probably the hardest ones to plot. So we get a break frequency then as a result, and we get a phase representation too that breaks at that frequency also as a result, kind of very, very sharp, but that's what the asymptotic representation of a second order term looks like. It's a little bit disingenuous, but that's the way it looks. Okay, that's for omega tau equals 1, if you will, and of course tau equals 0.1. So T2, magnitude T2 in dB is minus 20 log to the base 10 of 2 eta, and that gives us 8 dB as a result. Draw the composite magnitude. At omega tau equals 1, we had that representation, and we draw the composite magnitudes now as a result, which are much more complicated to say the least. Dotted green line, followed by a break, followed by another dotted green line, phase representation overall, if you will, and then the dotted phase representation, break, another break. Behavior close to the corner of a conjugate pole 0 is too dependent on the damping ratio, and a computer evaluation is better. And perhaps in general, this is not a great way to plot it by hand because it's much more complicated as a result. Let's evaluate that second order polynomial term that we just got done, but let's do it with MATLAB because it seems to be much more complicated to be done graphically. So here's the MATLAB representation. The numerator is 25, 0. Notice that we have to have a numerator polynomial. It's a first order polynomial and it does not have a constant term, doesn't have a +1, so we have to put a 0 there. For denominator, we're going to do it easy. We're going to form each of those terms separately in brackets. So one term happens to be a first order polynomial, so its coefficient is 1 and the constant is 0.5. We're not even putting it in normal form. We're just using it as given. And the second polynomial has a magnitude of 1. That's the second order polynomial. It has a magnitude of 4 for the first order term and a magnitude of 100 for the constant. Notice the use of the bracket terms with a comma in between and the parentheses around the whole argument with the function called CONV. That's polynomial multiplication. You can then have MATLAB do that by hitting carriage return, and you get the denominator polynomial is 1, 4.5, 102, and 50 in the order that we would expect from the highest order down to the constant. So we would end up with the representation of a third order polynomial whose third order coefficient is 1, second order is 4.5, first order is 102, and the constant term is 50. If you don't quite remember that, the percent sign is a comment statement. So you can liberally put comment statements in your MATLAB code, which may help you recognize what's going on. But the real work is done by the freq s term, numerator, comma, denominator, as we saw. And when we do that, it plots it, and it plots it very well, and in fact, very accurately. Much better than trying to do it by hand. Okay, so let's go back to MATLAB and type clear all, which closes the workspaces and closes any open figures. And then type figure 1, which opens one figure window, not strictly necessary, but we can do that. We could define W equals log space, which is now going to define the x-axis, which runs from 10 to the minus 1 to 10 to the third, with 200 points total. That's what the argument of log space is, 1, 3, 200 in MATLAB. We can put in our representation of our function directly, complete transfer function. We can then subplot, divide the figure in two for the top part, and do semi-log and put the magnitude there. That's how we can get the magnitude of phase plots. So here we get the magnitude plot. This allows us to not form the polynomial, but just analyze the frequency response directly in MATLAB. And then we can put a grid on if we want with proper titles and labels, Bode plot, magnitude response, for example, which we can do, and basically make it look a little bit nicer. We can repeat then for the phase, Bode plot phase response, and the end results for the two figures then look like this. We can also use in MATLAB Zoom to specify a specific region of interest. And we can compare it with the default that we got, and we notice that there. Let's sketch the magnitude characteristics of a second order polynomial in the denominator, this time with standard forms, as far as we can see. We know T2 has this standard form, and we do see the 1 plus, so that's good. We can find tau equals 1/12 by inspection, and 2 eta tau is 1/36, or eta is 1/6. We can then go with our sketching of the magnitude characteristic. We want, as we've done before, we'll take the 0.2 and the j omega, and we'll bring them together to find it where their representation, in this case for omega equals 0.2, and the value at that time, and we could plot it asymptotically between 0.2 and 2, and there's our representation. We'll have 0 dB at 0.2, and it'll go down to minus 20 dB because it is essentially a pole with the j omega term in the denominator at 2. The j plus 1 is a 0, breaks at 1, asymptotically goes out to 1, then breaks. 20 dB per decade between 1 and 10 goes up to 20. The polynomial term, second order, has been analyzed. We know that it goes out essentially to the first break, which is around 12, and then breaks. And omega tau equals 1. We find that magnitude of T2 dB is minus 20 log to the base 10 of 2 eta, or if you will, about 9.5 dB as a result. And that gives us our magnitude response to the first break, to the second break, and to the third break as a result. Minus 20 dB per decade, minus 40 dB per decade overall. 0 dB per decade occurs in the middle because the two first order terms essentially interact. And the minus 20 dB per decade and the plus 20 dB per decade produce 0 dB per decade starting around 1. As far as the representation is concerned, we know that 12 is a breakpoint, and that gives us the magnitude characteristics. The phase characteristics are much more complicated. We can certainly do it in MATLAB, and here are the MATLAB representation of the frequency response, magnitude, and also the phase. Now we want to look at determining the transfer function from the Bode plot. This is an inverse problem of determining frequency characteristics. We're only going to use the composite asymptotes, though, of the plot of the magnitude to try to postulate or guess at the transfer function. The slopes will provide information, of course, on the order by how many decibels per decade they're actually either increasing or decreasing. So here's an example. I have a magnitude plot, minus 20 dB per decade, breaking at some particular frequency. Then it seems to level out, and then it breaks again, and then it breaks at 40 dB per decade. From this, we're trying to infer what the frequency response of the transfer function really represents. Well, the first thing is to look at the extreme left-hand side, where we have 20 dB down at very low frequencies. So therefore, there must be a constant K0 that represents this particular value, which is different than 0 dB. And that would give us a value for K0. And K0 is, in fact, 20 in this case. For the second order term that we next have at B, we have minus 20 dB per decade breaking at a frequency. So we'll take a simple pole. It's supposed to be at 0.1 nominally. Graphic is a little off. So therefore, it's j omega divided by 0.1 plus 1 in standard form, 1 over that because it's a pole. At C, we know something happens, and we know that there must be a simple 0 at that location to cancel the pole so that it now becomes a asymptotically flat response. And therefore, j omega divided by 0.5, because we'll assume it's 0.5 radians where the break occurs, and plus 1 in standard form. At point D, there's another break, 20 dB per decade, so that's a simple pole then at 3. J omega divided by 3 plus 1 inverse, that's a pole. And finally at E, there must be another simple pole at 20, producing an overall 40. Remember, it's 20 dB per decade even without E occurring, but when E occurs, it is an additional 20 dB per decade, or a total of 40. So that's j omega divided by 20 plus 1, standard form, inverse, because it's a pole. So now we can write the overall gain function that this Bode plot represents by bringing those terms together. If the slope is minus 40 dB, we'll assume double real poles unless we're giving more data, but hopefully we can do that at the time. But the minus 40 dB in this case is not minus 40 dB. It's the summation of two minus 20 dBs per decade acting together. Let's now determine the transfer function from a composite magnitude asymptotic plot. First, we'll look at A, and we notice that A is a minus 20 dB per decade slope, which breaks at 5, whose value is 0 dB. So that means there's a pole at the origin, which crosses 0 dB line at 5, and that would be 5 over j omega. Omega equals 5. We get 1 over j, if you will, and that's our 0 dB with a magnitude of 1 when omega equals 5. And of course, pole at the origin means that it's a 1 over j omega term, first order. Then we get a break from minus 20 dB per decade to a flat asymptotic value. So we know that means that has to be a compensating 0 at 5 to change the slope to 0. Then at C, we would get a pole at 20, which would then continue the minus 20 dB per decade asymptotic behavior. And then we would need some other compensation at 50 to make it flat again at D. So there must be a 0 at D at 50. And finally, there must be another break at 100, another pole at 100. As a result, minus 20 dB per decade. Notice these are all first order terms. It's relatively straightforward to do because they're not as complicated as quadratic and higher order polynomials. So from the information that we just gathered, we can then write the transfer function in standard form anyway. Notice every term has +1 in it. We could straighten it out if we want, but that's certainly the form. There's the 5 over j omega. There's the 0 at 5. There's the 0 at 50. There's the pole at 100. And last but not least, there's the pole at 20. This concludes sections 1 to 2 of Chapter 12, Variable Frequency Network Performance.